Okay, these are the topics today. I combine these two sections to present. In the first topic, I introduce you the concept of subspaces of Rn. And the second topic, I explain what is a basis for a subspace. And the third topic, associate with any matrix. There are two subspaces. There are two subspaces. One is column space, and the other one is no space. No space. Yeah. Take a review first. We usually call R3 a three-dimensional space, and a plane in R3. This plane passes through the origin. We call a plane through the origin in R3 two-dimensional subspace of R3. And a line in R3. This line passes through the origin. We call that line one-dimensional subspace of R3. Now, let me generalize the subspaces of R3 to the subspaces of Rn. Here is the definition. Suppose H be a set in Rn, a set of points in Rn. If H has the following three properties. Number one, origin 0, the 0 vector is in H. Yeah, this rotation means inside H. Property number 3, any two vectors in H for any two vectors in H, U and V, then the sum of the two vectors is still in H. This property, we call it H is closed under vector addition. C, for any scalar, say C, and any vector from H, C times the vector is still in H. Property C, we call it H is closed under scalar multiplication. If this set H has these three properties, we call the set a space. Then H is called a subspace of Rn. Subspace usually or simply space. Sometimes we just call H is a space. Actually, it is a subspace of Rn. It is part of Rn. This definition, simply speaking, what is a subspace of Rn when the set is closed under vector addition and scalar multiplication? Then the set is a subspace, simply speaking. Last time I showed you some examples about a subspace of Rn. More examples today. Okay. More examples today. Okay. Examples. Number one. Let V1 and V2 be two vectors in Rn, and let H be the set spanned by V1 and V2. Recall that the set spanned by V1 and V2 is the set of all linear combinations of V1 and V2. Yeah, all possible linear combinations, put them together, we have a set. The set is called the set spanned by these two vectors. Then this H is a subspace of Rn. How to see this? Go back to the definition. We need to show that this set has the three properties. So why H is a subspace of Rn? Number one, 0 is in H. Why 0 is in H? Because 0 is a linear combination of V1 and V2. How to see that? 0 is the scalar 0 times V1 plus the scalar 0 times V2. 0, this vector is a linear combination of V1 and V2. Therefore, so 0 is in H. Property A is satisfied. Now, property 2, B. Arbitrarily pick two vectors from H. The sum should be still in H. B. Arbitrarily pick two vectors. Say U. U is from H. H is the set of linear combinations of V1 and V2. So U is a scalar. Say alpha 1 V1 plus beta 1 V2 alpha 1 beta 1 numbers. Pick a second vector. Alpha 2 times V1 beta 2 times V2. Yeah, these two vectors are from H. Now let me make a sum. U plus V is equal to alpha 1 V1 plus beta V2 plus alpha 2 V1 beta 2 V2. I combine this term and this term. Then I get alpha 1 plus alpha 2 times V1. Combine this term and this term. Then I get beta 1 plus beta 2 times V2. See? This is a linear combination of V1 and V2, right? Alpha 1 scalar plus scalar, still a scalar. Scalar plus scalar, still a scalar. So this is still inside H. Therefore, the second property in the definition is satisfied. Now, property C, arbitrarily pick a scalar, arbitrarily pick a vector. And let's see, C times the vector is still in H or not. Property C, pick a scalar C and pick a vector from H. Say the vector is a linear combination, V2. Okay, now I compute C times this vector. Then I get C times alpha V1 plus beta V2. Distribution. Then I get C times alpha. A number times V1. C times beta times V2. See, this is a linear combination of V1 and V2. So inside the set H. Therefore, the three properties in the definition all are satisfied. Conclusion is H is a subspace of RON by definition. Example 1. Now, example 2. Let V1, V2, Vk be vectors in Rn, and let H be the set spanned by these k vectors. This is the set of all possible linear combinations of these k vectors. Then H is a subspace of RON. Yeah, this set has the three properties in the definition. Number 3. This example is an example about a set that is not a subspace. A line. Let me denote the line by L. Not through the origin of Rn. Now this time, this 9 is not a subspace of Rn. Let me draw a diagram. Say, suppose this space is Rn. Origin is here. Oh, origin. Origin is this point. All the entries are zeros. Okay, now a line not passing the origin. Yeah, this 9. This time, this 9 is not a subspace of Rn. Why? Because this 9 doesn't have all the properties in the definition. Solution. 0 is not in L. Therefore, by definition, this 9 is not a subspace. And also easy to see that this 9 is not closed under vector addition. Let me pick 2 vectors. Pick 2 vectors. Yeah, say, pick this point on the line. Let me draw an arrow. Yeah. Then the sum of these 2 vectors, sum parallelogram. The sum is this vector. This vector clearly not on the line. A vector and this point, they are the same, identical. So this point here is not on the line. So the 9 is not closed under vector addition. And also this 9 is not closed under scalar multiplication. Easy to see that. Say, pick a second vector. Say, pick a vector on the line and pick a scalar. Say, let me denote this vector by v. A scalar, say for example, -1 times v. This vector is not on the line. This vector is this vector, -v. Yeah, this point not on the line. So when a line not passing through the origin, that line is not closed under vector addition and scalar multiplication. But we have 3 properties in the definition. When one of the properties is not satisfied, the set is not a space, not a subspace. This is example 3. Now let's example number 4. Example number 4. Let A be an M by N matrix. M by N matrix. And I let H be the set of all the solutions of this equation. All right, A is M by N. X is M by 1. This 0 is M by 1. H is the set of the solutions of this equation. The solution is in Rn. Yeah, X is in Rn. Then H is a set of Rn, not a set of Rn. H is a set of Rn. And H is a subspace of Rn. That means this set has the free properties in the definition. How to see this? Solution. To see H is a subspace of Rn. Free properties. Number one, let me see. 0, the vector is in the set H or not. Because 0 solve this equation. A times 0 is equal to 0. So 0 is a solution of this equation. So 0 is in H because H is the set of all solutions. So 0 is in H. Property A in the definition is satisfied. Now, pick two vectors, U and V, from H. I want to see whether U plus H and U plus V still in H. Because U and V from H, we have A times U is 0. A times V is 0, right? U and V are solutions of this equation. So we have these two equations. Now, make a sum. If this sum also solve this equation, then the sum is in H. Now, let me see whether or not A times this guy is 0. By distribution, I have A times U plus A times V. But A times U is 0. A times V is 0. So 0 plus 0, 0. Therefore, the sum solves this equation. The sum is a solution of this equation. So, conclusion, U plus V still in H. The second property in the definition is satisfied. Satisfied. Okay, now property number C. Take a scalar. Take a vector from H. Now I want to see whether C times the vector still in H. H is the set of all the solutions of this equation. Now have a check. A times this vector. The scalar C can be moved on. But A times V, V from H, A times V is 0 vector. So any number times 0 vector is 0 vector. Therefore, C times V solves this equation. So conclusion, C times V in H. Because all the free properties are satisfied. Conclusion. Conclusion. H is a subspace of Rn. Rn. We usually call this special subspace the null space of matrix A. Of matrix A. The null space of matrix A. Yeah, this H. The set of all solutions of this equation is the null space of matrix A. Example 4. Now, the next example is not a subspace. Example 5. Let A be an M by N matrix. Again, I let H be the set of all the solutions of this equation. Now, this time, right-hand side is non-zero. B is non-zero. Yeah. So this equation is a non-homogeneous equation. Now this time, then H is not a subspace of Rn. How to see is have a check with the free properties in the definition. When one of the free properties is not satisfied, the set is not a subspace. Okay, property A. Let me see whether zero vector is in H or not. Okay, now plug in zero in this equation. I want to see whether zero solve this equation. A times zero is equal to zero, not equal to B. Therefore, zero is not a solution of this equation. Therefore, so zero not in H. Now, conclusion. Conclusion. H is not a subspace of Rn. Actually, this H is not closed under addition. Say a peg U and V from H. Then H is the set of all the solutions. Then A times U is B. A times V is B. Now, let me make a sum. I want to see whether this sum is a solution of this equation. Okay, now A times U plus B. Distribution. I get A times U plus A times B. It is B plus B. But B plus B is 2 times B, not equal to B. So U plus C not in H. In other words, H is not closed under vector addition. And also H is not closed under scalar multiplication. Say peg a scalar, say peg 2 a scalar, and peg a vector in H. Now 2 times U. Let me see whether or not 2 times U is a solution of this equation. A times 2 times U. I move out the scalar 2. But A times U is B. 2 times B clearly not equal to B. So therefore, 2 times U is not in H. So H, it is not closed under scalar multiplication. But anyway, one of the three properties is not satisfied, then the set is not a subspace. Example 5. Yeah. This is topic 1. Second topic. Second topic. Spanning set. Smallest spanning set. A basis. Topic 2. Every space or subspace has a basis. Now, I want to explain what is a basis. Take a look at the following example. Example 1 under topic 2. And then V1 be 1, 0. 2-dimensional vector. V2 be 0, 1. V3 be -1, 1. V4 be 1, 1. 4 vectors all from R2. Okay. Then can you see that R2 can be spanned by these 4 vectors? Can you see that? How to see R2 is the set spanned by these 4 vectors? How to see this? Arbitrarily pick a vector. Say vector U, arbitrary pick. Okay. Arbitrary pick. Say A and B scalars. Pick a vector from R2. I want to see whether this vector is spanned by these 4 vectors. Spanned by these 4 vectors means a linear combination of these 4 vectors. Okay. Now, let me write U. U is AB. I write this as A times 1, 0. This is a V1. B plus 0, 1. And then a linear combination of these 4 vectors. And then 0 scalar times -1, 1. 0 times 1, 1. Yeah. In the V rotation, this is A times V1. B times V2. 0 times V3. 0 times V4. Yeah. Any vector in R2 can be written as a linear combination of these 4 vectors. So any vector in R2 is spanned by these 4 vectors. Therefore, conclusion, R2, this two-dimensional space, can be spanned by these four vectors. Now we call the set of these four vectors spanning set of R2. Yeah, these four vectors, put them together, we have a set. The set is a spanning set of R2 because all the vectors in R2 can be spanned by these four vectors spanning set. Okay, now this spanning set has four vectors. Let me drop one vector. Okay, now drop one vector. Okay, we have V1, V2, V3, V4. Drop one. Say drop V4. Drop V4. Say drop V4. Then can you see that R2 is still spanned by the remaining vectors? How to see this equation? How to see this equation? Arbitrarily pick a vector from R2. Let me see whether or not this vector can be written as a linear combination of V1, V2, and V3. Let me write U A times 1, 0. 1, 0 is V1. B times 0, 1, V2. And 0 times V3. What is V3? Let me write 1, V3. This is A times V1 plus B times V2 and 0 times V3. So any vector in R2 is a linear combination of V1, V2, and V3. Any vector is spanned by V1, V2, and V3. So conclusion. So R2 is the span of V1, V2, V3. Therefore, the set V1, V2, V3 is a spanning set of R2. Now, let me drop V3 from the spanning set. Now, drop V3 from the spanning set. Then it can be seen that R2 is still spanned by V1 and V2. Any vector in R2 is a linear combination of V1 and V2. Therefore, the set of V1, V2 is a spanning set of R2. How about we continue the dropping process? from this spanning set, how about let me drop V2? Okay, now drop V2 and ask yourself, then R2 is question mark span by V1. Now this time, I don't think so. Okay, what is V1? 1, 0 is V1. How to see? R2 is not spanned by V1. V1 can only span a line through the origin. Let me pick this vector, say 0, 2, this vector. I don't think this vector can be spanned by V1. Then 0, 2 is not equal to a number times V1. What is V1? 1, 0. Yeah, we cannot find a number so that this equation is true. So this vector cannot be spanned by V1. Therefore, this time, R2 conclusion not equal to span. Therefore, the set of the single vector V1 is not a spanning set of R2. Oh, it turns out that this spanning set is a smallest spanning set of R2. This is a smallest spanning set of R2. We call it a smallest spanning set is called a basis of R2. Yeah, this set is a basis of R2. Smallest spanning set is called a basis. In this solution, I drop V4, drop V2, V3, and drop V2. You can drop other vectors. Say drop V4, then drop V2, and drop V1. Okay. If I change the dropping process, it can be seen that V1, V3, this set is also a smallest spanning set. Is another basis of R2. So the conclusion is a space can have more than one basis. More than one basis. Now let me make a summary and put the summary as into a definition. Now definition. Okay. Part A. What is a basis of a subspace? Let me name the subspace H of Rn. What is a basis of a subspace in Rn? It is a smallest spanning set of H. In other words, a basis of H is a linearly independent set. A basis is a set of vectors. Those vectors are linearly independent to each other. Linearly independent to each other. In other words, no vector can be spanned by other vectors independent. A basis is a linearly independent set. The set span H. Linearly independent set. In the set, no vector can be spanned by the other vectors, and the set spans H, the subspace. Then the set is called a basis. This is part A of the definition. Now the second part. Okay, part. Okay. A subspace or simply a space can have many bases. A subspace can have many bases. However, it can be proved that the number of vectors in each basis must be equal, the same. Theoretically, we can prove this. This same number is called the dimension of, how about let me give a name to the subspace, say H. The same number of vectors is called the dimension of the subspace H. R3, we usually call it three-dimensional space. Why? Because each basis in R3 has three vectors. Only three vectors can span R3. Two vectors cannot span R3. A plane in R3, a plane through the origin. A plane in R3 can be spanned by two vectors. A basis of a plane has two vectors. So plane is a two-dimensional space. A line through the origin in R3 can be spanned by one vector. A basis of a line contains only one vector. So a line is a one-dimensional space. So the same number of vectors in a basis is called the dimension of the space H. Yeah, definition here. Okay, next, let me show you examples about this definition. Take a look at some examples. Example, what number? Example 1, example 2, under the second topic. Example 2. And then V1, 0 to level 1. It is in arrow free. V2, 2 to 0, also in arrow free. V3, 6, 16, -5. Okay, now and then H be the set spanned by these three vectors. It is a subspace of arrow free. This is a subspace of arrow free. Because H spanned by these three vectors, then the set put these three vectors together. We have a set is a spanning set of H, because this set spans H. It is a spanning set. However, but it's not a basis, because this set is not the smallest spanning set. How to see? It's easy to see that V3, this vector, is equal to 5 times V1 plus 3 times V2. That means that, yeah, 3 vectors. Oh, it turns out that the third vector can be spanned by the first 2 vectors. Yeah, easy to verify this. So therefore, I can drop V3 from the spanning set. So H, yes, spanned by V1, V2, and V3. But V3 is spanned by V1 and V2. So I can drop V3. Therefore, V1, V2 is also a spanning set of H. Now, V1, V2, let me see whether we can drop one vector. Now this time, I don't think so. V1 and V2 are linearly independent this time. How to see V1, V2 are linearly independent? To see V1, V2 is linearly independent. Solve this vector equation. This vector equation. If the vector equation has only the 0 solution, then V1, V2 independent to each other. Yeah, solve this, then we see that only 0 solution. 0 solution. Yeah, when you solve this vector equation, you will see the solution is 0, 0. So therefore, V1, V2 is a linearly independent set. That means that you cannot drop any vector from this spanning set. This is a smallest spanning set. So conclusion, V1, V2 is a basis of H. Because this basis contains two vectors. So dimension of H is equal to 2. Yeah, this H is a two-dimensional subspace of R3. That means that the graph of this H is a plane, two vectors, a span a plane, is a plane in R3. The graph is a plane. Example 2, example 3. Example 3. Let H be the set of vectors of this form. A number. Second number is equal to the first number. Third number can be different, where B1, B2 are arbitrary numbers. Yeah, vectors of this form, put them together. We have a set, I call the set H. Then it is easy to see that this H is a subspace of R3. Have a check with the three properties of the definition about a subspace. Easy to see that this H has all the three properties. So H is a subspace of R3. Now I want to find a basis for H. To find a basis of H, I write each vector in H as some linear combination. Yeah. Let me write this vector as a linear combination. Let me see. Let me split the vector into this sum. Right? The right side is a sum of two vectors. Add the corresponding entries. Then I have the left side. Right? Then I take B1 out of the first vector. B1 times 1, 1, 0. And take B2 outside the second vector. Each vector in H is a linear combination of this vector and this vector. So H spanned by these two vectors. So H spanned by 1, 1, 0, 0, 0, 1. Yeah. Therefore, these two vectors is a spanning set of H. Now, whether or not this spanning set is a smallest spanning set, to see this, we need to have a check whether or not these two vectors are linearly independent to each other. Okay. To see, how about let me give names. Call this V1, V2. To see whether this set is linearly independent. How to see? Solve this vector equation by definition. All right. A linearly independent set. We need to, by definition, we need to solve this vector equation. Now solve this vector equation. 1, 1, 0. X2, 0, 0, 1. 0, 0, 0. Solve it. The left side is, let me add the left side. The left side is x1, x1, x2. Now is equal to 0, 0, 0. So implies that x1, x2 must be 0. Yeah. 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 So this vector equation has only 0 solution. Therefore, this set is a linearly independent set. Yeah, the vectors in this set independent to each other. So therefore, this is a smallest spanning set. It is a basis. Conclusion. Conclusion. V1, V2 is a basis of H. So dimension of H is equal to 2 because the basis contains 2 vectors. Dimension is 2. So if you plot the graph of H in R3, you will see a plane. A plane. The plane passes through the origin and passes through this point 1, 1, 0, and also this point 1, 0, 0, 1. Yeah. Okay. Example 2. Example 3. One more example. Example 3. And then U be 1, 4, 0. A vector in R3. V be 2, 8, 0. Also a vector in R3. Now, let H be the set spanned by U and V. Usually, 2 vectors span a plane in R3, but not this case because these 2 vectors are on a line. So, in this example, this H, the graph is just a line. Yes, the set of UV. Yeah, put UV together, we have a set. The set is a spanning set of H. But this spanning set is not a smallest spanning set. Why? Because easy to see that V this vector can be spanned by vector U. How? 2 times vector V, U. So therefore, H spanned by U, V. It turns out that I can drop the vector V from the spanning set. Drop vector V. So conclusion, So the set of the single vector U is a basis, smallest spanning set of H. If you plot the graph of H, you will see, plot the graph. Imagine this is an arrow free. Origin is here. Origin is here. Let me plot vector U. Vector U is this vector. Vector U. Vector V. Vector V is this vector. These two vectors lie on the same line. So these two vectors span just a line for the origin. One-dimensional subspace. Okay. So therefore, conclusion is a dimension of this space H is just one, because the basis contains only one vector. Topic 2. Let me see topic. Topic 3. Topic 3 says that associate with a vector, a matrix, any matrix. There are two subspaces. One is called column space. The other one is called null space. Let me introduce you the definition about these two spaces. Topic 3. Topic number 3. Mathematics always definitions, then theorems. Okay. When you solve a problem, always go back to the definition. Definition. Let A be any matrix, be an M by N matrix. Now A. Let me cut the matrix into columns, and then A1 be the first column, A2 second column. How many columns? I assume the matrix, the size is M by N, N columns, AN. Okay. Below the columns of A. Okay. Now let H be the set spanned by the columns. By the columns. All right. Please note that because our matrix A is M by N, each column has M entries. So actually, each column is in, this rotation is in ROM, not in RON. Okay, each column is in ROM. So the set spanned by vectors in ROM, the set is a set in ROM. Okay. Then H is a subspace. A set spanned by vectors is a subspace. A subspace of ROM, not RON. ROM, okay? Because each column is a vector in ROM. So these vectors can span a set in ROM. H is a subspace of Rn. We call H the column space of matrix A. The notation denoted by COL, column of A. Yeah, this is a column space, means this set spanned by the columns. Null space. What is null space of matrix A? B. Then H be the set of all the solutions of this equation, homogeneous equation. From one previous example, we see that H is a subspace. Now, take a look. Okay, the size. Okay, matrix A, the size is m by n. Solution, the size is n by 1. Right side, of course, m by 1, not n by 1, the right side. Okay, because A m by n times n by 1 cancel the middle n, so we get m by 1. Let H be the set of all the solutions of this equation. Then H is a subspace of, now this time, Rn, because H vector in H is in Rn. Okay. We call this H the null space of matrix A. The notation is denoted by null, NUL, A. Yeah. Definitions in mathematics. Let me emphasize again, important. Okay. So whenever when you want to solve a problem about, say, column space, null space, go back to the definition to see what the meanings of column space and null space. Okay, now let me stop here today.